Have you ever talked to an AI and it said something so genius, so sophisticated, so profound that it made you go, wow, wonder how a computer can even do that? Well, you're in the right place because in this video, I'll explain the math behind LLMs so that you, yes, you, could go on to create something similar to ChatGPT. So without any further ado, let's dive in. A large language model is a type of neural network trained to predict the next word in a sentence. The basic loop is simple. Give it text, it predicts what comes next, that prediction gets added back into the input and it keeps going until it's done. Everything else, how it's built, what it was trained on, and how it's fine-tuned, is all just to make those guesses better and more accurate. Now, computers don't understand words, they only understand numbers. So the first step is converting text that the computer can't understand into numbers that the computer can actually use. Before we go on though, it's important to note that large language models don't actually work with full words. They break text into smaller pieces called tokens. A token is just a chunk of text. It could be a full word, part of a word, or even punctuation. The reason we break words into tokens is to keep the vocabulary more manageable, among other things. Note that throughout this video I might use word instead of token, but keep in mind that the model doesn't cleanly separate text into words like this. Unfortunately, a single number for a word is inflexible enough. So instead of representing each word with a number, the model represents them as a vector, which is just a long list of numbers. You can also think of a vector as a point. In this case, the point is in 2D. In order to get these vectors from the token IDs, the LLM uses something called the embedding matrix, which you can think of as a giant lookup table. To use this lookup table to retrieve the vector for our word, we just grab the associated row from the matrix. Now the reason we prefer vectors over token IDs is that once we turn words into vectors, similar words end up having similar values. Once we transform words into useful vectors, they enter an embedding space. In embedding space, words with similar meanings end up close together. For example, dog is near puppy and car is near truck. And relationships can even form directions in space. For example, if you take the difference between king and man and add that to woman, you would get queen. The reason we want the model to do this in the first place is because it allows the model to better understand what each word means. You should note that this embedding matrix initially starts out as random and the model has to figure out the right values for each row. I should also note that the visualization is in 2D, but in practice, the embedding space is in several thousands of dimensions. Basically, this means that the vectors we get from our embedding matrix will have a lot more than 2 values. The exact number of values in the word vectors depends on how complex we want the model to be, but it requires a lot more computation to train and use. A lot of other things the model uses, called parameters, will also start off as completely random and get learned by the model. I will explain this idea of learning towards the end. Problem with our implementation is that so far every word has a general meaning, but meaning depends on context. Take the word light. In the sentence turn on the light, it means illumination. In the sentence this box is light, it implies not heavy. So the same word has different meanings. Therefore, the model should update each word using the words around it in order to fully understand sentences. This is where attention comes in. Attention lets the model update each word's meaning by looking at the other words in the text. Attention allows the model to gain context. In order to use attention, each word vector is transformed into 3 more special vectors, which are the query, key, and the value vector. Using the key and query vectors, we could create an attention table, where rows are queries, where each word asks who is relevant to me, and columns are keys, where each word offers its info. For example, chased has a high value with dog because chased describes what the dog is doing. Note that the bottom triangle is cut out because it wouldn't make sense for words to interact with themselves or words that come after it. Now we apply a softmax column by column. The softmax takes in a vector and outputs a probability distribution that allows us to actually use the values in the table. Columns will now add up to 1 nicely and negative infinities will be zeroed out. This final table is used to blend the value vectors. Therefore, value vectors are the context of the word, and query and key vectors decide how much of that meaning the current word gets. Notice how the word the appears twice, yet it has 2 different vectors. This is because we add the positional embeddings to the word embeddings, which encode the position of each word in the sequence. By including position information, the model can better understand context. Now, instead of running attention once, the model does it multiple times in parallel. Each parallel attention process is called a head. Different heads do different things. One might update nouns with adjectives, one might update verbs with adverbs, and one might update nouns based on verbs, like in the previous example. In the end, their results are combined. To recap what we have till now, words are first translated into numbers, which are translated into vectors, because a single number is too simple. Then we pass each word through a head of attention where each word learns context, and then the results are collected. Now, after attention gathers this information, each token passes through a small neural network called an MLP. Basically, MLPs help the model refine the meaning of each word. Together they form a single layer, and the LLM stacks lots of these layers in order to be as accurate as possible. And that's basically it. Our LLM is just a bunch of these layers stacked on top of each other. Now, I covered MLPs in the last video, so I won't go deep on the mechanics here. Basically, they are structured like this, and information flows through each layer and is multiplied and added by the appropriate parameters for that layer. After the final layer, the model has a rich context-aware vector for each word. To predict the next word, the final vector is multiplied by another learned matrix. This produces a probability for each word in the vocabulary. The model picks a word based on the probability and the process is complete. All those matrices I mentioned earlier, like the query, key, value, or embedding matrix for example, start off as random. To make them accurate, we train the model on a huge amount of text. Training basically just means we give the model some text, it guesses the next word, and based on the probability distribution it produces, we nudge each parameter in the model by how much it contributed to the mistakes. Doing this for billions of times, and eventually our model will output coherent sentences. Now we're gonna look at Andrej Karpathy's NanoGPT, because it ties into everything that I've talked about, and because I said so. This function will produce two sequences, one called input data and the other target. For this sentence, they might look like this. Basically, for some text, the function returns each possible input and output. Using the inputs, the model will have to guess the output. Note that the block size defines how many words the model can see at once. Ideally, the block size is high, so the model can understand large sequences of text. That takes a bit of toll on the GPU. The class for a single head of attention looks like this. In the init method, we initialize the query, key, and value matrices. Note that each head gets its own separate matrices. Here, we calculate the attention table I showed earlier. Then, we zero out certain values so that future words don't influence past words. Now at this step, the attention table doesn't actually produce probabilities. We still need to apply softmax in order to get a distribution. Then we blend the value vectors by the table we just created and we're done. Note that dropout is a technique where we randomly set some of the parameters of the LLM to 0 so that it trains better. Multi-head attention is pretty straightforward. We just run the data through multiple attention heads and then we group the data. Note that there's some stuff we're doing here about resizing, but that doesn't really matter too much to what we're trying to do, so we can ignore it. Feed forward is just the MLP layer I told you about before. Again, not too much going on here. The block class is the same thing as the layer in our notes. We first apply multi-head attention, then we run the MLPs. Normalization for us basically just makes sure that the word vectors are in a reasonable range. Using everything we have, we can tie it into one GPT class. The token embedding table turns the token integer IDs into vectors. The position embedding table tells us the position of each token, and its use will be made clear in a second. Blocks is our stack of repeating multi-head attention blocks and MLPs. Forward is the main pass. It is responsible for training the model. We combine the position vector and the embedding vectors and then pass those into blocks, which again is just the attention and MLP layers. Then we normalize the output and extract the final probability distribution we get. Using this final probability distribution, we compute how wrong our model's prediction was, which we use to train the model. The code Karpathy uses for training the model looks like this. We first run a forward pass to grab the probability distribution the model guesses, and how incorrect the probability is. Then we optimize all the parameters of the network based on the results of the forward pass. The actual implementation of these methods is beyond the scope of this video, but I did touch on the subject in the last video of this series. In the generate method, we keep looping for the length specified in max new tokens to generate new tokens. All we really do is crop the context window to block size on a forward pass to get the probability distribution, pick a word from that probability distribution, and then repeat. Comparing our bot to GPT-2, they both have a very similar architecture, but GPT-2 has a lot more parameters and text to train on. Now, GPT-3 isn't open source, but from what I gathered online, for the most part, GPT-3 is just a scaled up version of GPT-2 with nearly 100 times more parameters. The other stuff includes the introduction of alternating dense and sparse attention patterns into the layers of the transformer. What this means is that instead of all the tokens getting modified in a head of attention, as they currently are, attention heads deep in the LLM will be both dense, where every word can influence every other word, just like normal attention, and sparse, where each word only influences a fixed subset of other words, like its nearest neighbors or words at regular intervals. The idea is that early layers handle fine-grained relations between words, and deeper layers need to capture broader, more abstract patterns across the whole sequence of text. By alternating between dense and sparse attention, the model can do both without the computational cost of running full attention everywhere. This becomes relevant when scaling up the model to bigger context windows because sparse attention lets the model stay efficient while still being able to reason across long distances when it needs to. Nothing really fun to talk about here, so let's move on to GPT-4. Now, I won't cover everything they did for GPT-4 in this video, but I will cover one thing: the mixture of experts. So remember how after a multi-head attention block, we sent our data to an MLP layer? Well, the problem with that is every token gets sent to the same MLP every single time, which is kind of wasteful. MOE basically asserts, what if instead of one big MLP, we had a bunch of smaller MLPs, and for each token, we only activate a couple of them? That's the core idea behind mixture of experts. We control which MLPs are used with a router network that looks at each token and decides which MLPs are going to be used. The other MLPs just sit out. They don't do any work for that token. Why is this useful? Well, because this allows GPT-4 to have a massive number of parameters, but we only use a fraction of those when we generate tokens. This allows us to have the power of a huge model without the full computational cost. This video was not meant to be a watertight explanation for what happens under the hood when you talk to ChatGPT. I have made a lot of simplifications in order to fit this into a 12-minute video. The structure and content of this video was highly inspired by the video series by Andre Carpathy and 3 Blue 1 Brown. I highly recommend those if you want to learn more.